Today we have a guest presentation and we're going to discuss plane waves. Let's introduce the presenter. I'll go and find him. Hello, Michael.
Hello, Matt. Good to see you.
Good to see you. This is Michael Lamoureux, Professor Emeritus from the University of Calgary and former head of the math department there. And we've been collaborating together for how long? About?
In our whole life, like 15 years or something like that.
15 years, and we've just finished doing, and we're still doing, an analysis of a different way to do calculus.
Yes.
So I'm very happy. Michael's very gifted at writing simulations. So we're going to start with the simulation right away in one dimension of waves. Let's have a look. You can see on the screen that we have our famous function traveling to the right along the x-axis with displacement. The actual amplitude of the wave is in the z direction, and the amplitude is a pulse, a Gaussian type bell-shaped pulse. And we started out the course with the analysis for this, so we eventually wrote it as f of omega t minus kx. In terms of the physics, we should be sure we've got the units right, because we can't take exponentials and functions of units. This has to be unitless, and it is units of omega, 2 pi over the period, 1 over time times time, no units. And this is 2 pi over lambda, 1 over meters, x in meters, no units, so that all makes sense. And we also know from our previous work that v is equal to omega over k. You can see that this wave is a beautiful traveling wave, but you know, Michael, I'd like to be able to do this in higher dimensions. So I'm going to pass it over to you to see if we can extend your simulations.
Well, if we want to look at the formula, of course, time is one-dimensional, so that doesn't change. We'll have to change x from a single variable to a double variable. So we think of it as a vector. So I can actually just change the formula by changing this to f omega t minus some vector k dotted with the vector x, which I can think of as x, y in 2 dimensions.
Yeah,
I'll hand this back to you.
kx and ky. So what is the velocity going to be in this case? Well, in this case, the velocity of the wave is going to be omega, but k is a vector. You can't divide by a vector, so the velocity of the wave will be the magnitude of k. And the reason we need to make this substitution from k scalar to k vector is because the energy is traveling normally in 3 dimensions, but we'll simplify it first to 2 dimensions. So this is the velocity, and this is quite an interesting vector. To see how this works, Michael, will you show us on your screen?
I can show you how this works. In fact, my little simulation here is really a side view of the 2-dimensional wave. And here we see a wave coming through. It's just this little row of a bump. That's the amplitude of the wave, and it travels from left to right. It's going in the x direction. What I've done is my k vector is this little red vector here. It's pointing in the x direction. That tells me where the wave is going. And of course, I set this up, Matt, so it would be a good demonstration. I can change the direction by just changing one of my variables here. So I'll change the vector. Now I have it pointing off in this direction. And you see the wave is now traveling in that direction. So I didn't change anything in the simulation other than this vector k.
So tell me, in general, this is a good way to do it because we can change the direction of your traveling hump by adding a y component to the x component, right?
That's right.
And that swings that little red vector around.
Exactly. So my k vector, you can think of it as 2 components, kx, ky. I just change those values, and that changes the direction that the wave is traveling in.
So in 2D, we would have, if we expanded this out in 2 dimensions, we'd have something like this, the k dot x.
That's right. You've got two components for k and two components for the x vector. So you got x and y multiplied by the coefficients kx and ky.
So if we put this equal to a constant, set it equal to a constant, say alpha, that means any x and y that satisfies this equation will have the same value of k dot x. And that means we'll be looking at that particular value, the argument of this function, this Gaussian. Do you have anything to add to that?
Yes, so one way to think about this is, at some point we want to talk about plane waves. You don't quite have a plane wave here, but what we can see on this diagram is the wavefront, sort of the peak of that little bump, it's a line. And so it's just a line that's traveling forward across our little space there. So this is, you could think of it as a wave with a single line for the wavefront. And it's the line that's traveling forward.
You know, that's interesting because we could look back at the one-dimensional case. So in one dimension, we're looking at a point traveling along the x-axis.
Right, that point is like the little peak of the waveform.
Any peak on that waveform will be a fixed point. Now we say the set of points that sit one dimension higher than a point, which is a line.
Right.
And then the next one will be a plane. So equation of the three-dimensional case.
So the three-dimensional case is going to look exactly like this, except now we will have to add a third component.
And now when this is a constant, that's
I
okay.
think we will have to write it down here because it's getting a little wiped out by our...
Oh, yeah, okay, so we have now if kxx plus kyy plus kzz equals a constant, I'll just say constant, we are no longer sitting on a line, but we're sitting on a plane.
Right.
Now I got a problem here because one of the dimensions in our graphics is used up by the amplitude of the wave. So in the current two-dimensional wave, we're using the xy plane for the variables and the amplitude is in z. So we've already used up 3 dimensions. That means when we go here, we're using up 3 dimensions as coordinates and we need a 4th dimension to represent the amplitude. That's impossible to do. What's your solution?
It sounds impossible to do, but what we can do is this thing, okay, we're thinking of x now as in 3 dimensions. So what's our 4th dimension? Well, we could use something like heat, or we could use something like electrical energy. Those are hard to draw on a computer screen, but what we can do is color. So our 4th dimension will be a color dimension.
Oh, and then we can represent 4 dimensions.
Exactly. So the color will represent the 4th dimension, and x, y, z are the positions. Now I even have a simulation of that. Would you like to see that, Matt?
Absolutely. I'm looking forward to that.
Let me bring it up quickly here. And here we have our simulation. I'm going to adjust a few things. Oops. Not what I want to do. It's a little tricky, but here's my z component. So I'll point that up because we like z pointing up. X is over here. So now I've got my 3 components. You can see, oops, stop rotating you. So I've got an x component. I've got a y component over here and z pointing up, the way we like things. Now, the tricky thing is, of course, how do you draw colors all through 3-dimensional space? If I had colors everywhere, you wouldn't see anything. So what I've done is I've taken a little slice of 3-dimensional space in the form of a sphere.
Oh.
And now what you see is there's a plane wave traveling through here. You think of the plane wave as intersecting the sphere. It starts at the bottom and then it works its way up. So these colors you see are actually a cross-section of the plane wave as it passes through the sphere.
So every plane has a different color. And I guess the blue, is the blue plane the maximum height of your Gaussian pulse?
That's right. Exactly like we had that little Gaussian pulse. Now the max point is the blue point.
Yeah, I noticed that it's symmetric about the blue line. So those are the tails of the Gaussian in yellow and green.
Exactly. Now you see this is going straight up. That's because I picked the k vector pointing in the Z direction. But I can actually adjust that. So you see here, this little blue dot is my K vector. I can move it to other places. Oops. This guy. I can move it down here. So the K vector is pointing off in this direction here. And now you see the wave is going in that direction.
Wow, that's really, really fabulous. It's very difficult to do this. I've not seen it in any textbook, and there's not enough emphasis, but we need to get a geometrical picture for plane waves to understand how they work in the Maxwell equations. And the nice thing about it is the function f that we use is a complex exponential, and so that's really nice to differentiate because its derivative is proportional to the function itself. And so with all this in place, it's very easy to do the differentiations, and we can study our Maxwell's equations using plane waves.
And hopefully that explains now why it's called a plane wave. You see the plane moving across the screen.
Good work.
Thank you, Matt.